abstract, then I lied. I decided to give a slightly different talk. So hopefully you'll forgive me, although there will be overlap. Okay, so we're still on Monday morning, so I should tell you what a cube complex is, because you're not going to learn about that until later in June, I guess. But since I wasn't invited to the cubes, I thought I'd talk about cubes today. So, so I'm interested in cat-0 cube complexes. A cat-0 cube complex is a complex built out of cubes of varying dimensions. You can take, they're all finite dimensional, but they don't have to be of the same dimension, glued along faces in the obvious way. So just take cubes and glue them together along linear isometries along faces. And then I would like to be simply connected. So it's the universal cover of something rather than the quotient space. And it satisfies Gromov's link condition. So in a cube, if you take a little epsilon neighborhood of a vertex, then you get a simplex with a natural, if you like, spherical metric, but I'm just interested in the combinatorics. So links of vertices are flag simplicial complexes. This is a non-positive curvature condition. So you should have, if you, for example, took a square and glued two adjacent edges together, then in the link there would be a loop. Okay, so that's not simplicial, and that's a little cone point, a point of positive curvature. So we don't like that. If you took two squares and identified the two sides of each along a corner, so you got a little, you would also get a point of positive curvature. That would be two edges in the link that shared two vertices, so not simplicial. And then the flag condition, well, if you took three squares and glued them together to make a little corner of a cube without the three cube in there, you would have an empty triangle, and that wouldn't be flag. So this is really ruling out some obvious positive curvature phenomenon. Okay, so it's a simply connected, non-positively curved cube complex. All right, so here's a somewhat strange question that I'm going to spend most of the talk talking about and motivating and trying to convince you that it's actually a good question. So suppose we have a cat-0 cube complex. Suppose we have some group K acting on X by, I'll say, cubical. So the metric on a cat-0 cube complex just comes from making every cube isometric to a Euclidean cube and then taking the induced length metric. So I'm acting on by isometries, but I also want to preserve the cubical structure, so cubes go to cubes. So if you took the plane and tiled it by squares, that would be a cube complex. There are plenty of isometries of the plane that don't take cubes to cubes. I'm not interested in those. I'm only interested in the isometries that also take cubes to cubes. Okay, so that's the setup. The question is, when is the quotient space X mod K also a cat-0 cube complex? Okay, so I say this is a slightly strange question because your initial reaction to this should be, or probably is, if you've never thought about this before, well, never. That's a ridiculous question. But I'm going to try and convince you that it's not a ridiculous question, that sometimes it holds, and then when it holds, it can be a very useful thing. Okay, so let me give you an instructive example, I hope. So let's suppose, so this is really thinking about what happens when X is one-dimensional. So a one-dimensional cat-0 cube complex is usually referred to by a different name, which is a tree. Okay. So we might have a group G, and it's going to be an amalgamated product. And suppose that we have normal subgroups of A and of B and of C, that should not be, that should be N sub C, that satisfies the compatibility condition. So if I intersect the normal subgroup of A with the edge group C, I should get the same as the intersection of the normal subgroup in B with the edge group C, and that should be this normal subgroup in C. Okay, so you may or may not be able to find such reasonable normal subgroups that are compatible in this way, but if you can, and I want to take K to be the normal inside the group G. include this because it's already in NA and NB. So group K, and then and T is cat zero cube complex, the Basset tree for the splitting. And if I take the quotient of T K, then that's a tree. In fact, it's a very obvious tree. It's the Basset tree for another amalgam. So this compatibility condition says that I can take the quotient of A by NA and the quotient of B, sorry, these are groups, so those quotients happen on the other side. And the quotient of B by NB, and they naturally each have a subgroup that is the quotient of C by NC. And I take that amalgam there, and that the Basset tree for this is naturally this tree here. So this is essentially follows from covering space theory for trees. But you can also see it more directly just via universal properties of amalgams and so on. Okay, so this is a case where you can have, in fact, a quotient of a cat zero cube complex by an interesting group be still a cat zero cube complex. Okay, so it's maybe not totally then ridiculous to hope that you might be able to sometimes do this. So I'm gonna. So what would we need? Okay, so this is a complex. I could take one of these cubical isometries and it could fix a cube as a set, but not pointwise. So you might think of a rotation of a square of order 4. Then the quotient is a triangle and it's not a cube. Okay, so that would be bad because I want my quotient to be a cat zero cube complex. So that's the first thing you would need. In this example here, that's what the without inversions is sort of doing for you in this case here, right? If you think about when you do Basset theory and you say you want to act on a graph without inversions, that says if you fix a cell setwise, you fix it pointwise. Okay, so this is the quotient of the tree by any group inside of G is going to be a graph. Yeah. Now, of course, you can get rid of that by subdividing in the one-dimensional case, and in the higher dimensional case, you won't be able to do that necessarily. The quotient could just be not a cube complex. Okay, what's the second thing you would need here? You need it to be simply connected. So I didn't tell you why this was a tree rather than a graph. But in fact, this is not so hard to ensure. In lots of situations, there's a theorem of Armstrong. I wrote down the date, 1965. I'm not going to write out that theorem because I'm running out of board space. Here's the theorem. Suppose you have a simply connected cell complex and you act by cellular automorphisms on it by some group G. And you want to calculate the fundamental group of the quotient space. So what that is you take the group generated by elements which stabilize points. Elements which stabilize points in the tree. So that you take the quotient of your group by that group generated by the things which act elliptically, stabilizing points. And that's the fundamental group of the quotient. So what you need in order for this to be simply connected is that the group generated by elements which fix points in the cell complex is the whole group. Okay, so over here, N sub A is a subgroup of A, so it stabilizes the vertex corresponding to A in the tree, and N sub B stabilizes the vertex by B. And I took a normal closure, but conjugates of things which fix points. So this is generated by elliptic elements. So that theorem of Armstrong, which works in total generality for cell complexes, tells you in this case that this quotient is a tree. And then it's an exercise once you know that to work out which tree it is, and it's this one. Okay, so this happens if and only if K is generated by elliptic elements. Elements acting on X which stabilize some cell. As a set. Once it stabilizes some cell as a set, it's going to stabilize its barycenter, and so it's going to fix a point. Okay. This is going to be, I don't want any elements that stabilize a cell as a set, but not stabilize them pointwise. That's what's going to make this a cube complex. Okay, and then there's a third condition. I need the link condition. Okay, and that's that in this complex, these links of vertices are flag simplicial complexes. This condition is by far the hardest to make satisfy. Notice in our instructive example, in a graph, links are all just a discrete collection of points. Okay, so that's flag simplicial complex, and there's nothing to check. Okay, so there's nothing to do in case 3 in this example here. Once the complexes are higher dimensional, then this is where the hard work may or may not, and I claim does, is to satisfy this condition here. Okay, so I'm not going to tell you how to make this be satisfied.
This way now. But do you have to look at the links of syntheses which are stabilized in low dimensions which are stabilized, then you want to look at the action of the stabilizer on the link that upstairs?
Yeah. Yeah, that's right. And it's essentially, it's some sort of ruling out certain kinds of configurations of multi-cosets of elements and stabilizers and so on. Yeah, so so making this happen, at least in the cubical setting, is some complicated multi-coset separability kind of condition. So I'm about to mention a theorem, and in that paper where we prove this theorem, we spell out exactly when this will happen. We give an algebraic condition. Okay, so since I'm about to start talking about some results, I'm going to mention the various results in this paper. Some of them will be joint with Jason Manning, some of them will be joint with Teddy Einstein, and the last one will be joint with Corey Bregman and Kejia. All right, so here is a situation where we can find interesting K, so that these, and given X and some ambient group like we started with in that situation, where these conditions are satisfied. So here's some setup. I have a pair G and a collection of subgroups of G relatively hyperbolic. I'm hoping that since there was at least one talk last week on relatively hyperbolic groups, everyone knows what these are. If not, well, interrupt me and we'll see what happens. That wasn't a threat, by the way. I genuinely don't know what will happen if you interrupt me. Okay. So I have a relatively hyperbolic group with some peripheral parabolic subgroups P, and I'm going to act on a cat zero cube complex. This is the assumptions that I'm making, and I'll talk in a bit about where these kinds of actions come from. And I want this action to be co-compact. As you can imagine from my discussion here in my illustrative example, I'm not interested in free actions, because I'm going to be looking at subgroups of G generated by elements that fix points. Okay, so there's nothing to say if it's a free action. Well, there's lots to say, but nothing in terms of this question. Okay, so this is the setup, and then I'm going to also suppose each element P in my peripheral family acts elliptically. So there is a fixed point for each subgroup. Okay, and then there's some geometry going on. So stabilizers, I'm not going to assume the stabilizers are parabolic elements, although that will come later. But rather, suppose cube sigma in X, the stabilizer in G of sigma is full relatively quasi-convex. Okay, so I'll tell you in words what this means without writing anything down. So here, full is a condition on intersections with the peripheral subgroups. Relatively quasi-convex is a general, and I'll tell you what that condition is. Relatively quasi-convex is a generalization of quasi-convex for hyperbolic groups. In this case, you can just say that it's a quasi-isometrically embedded subgroup. And it has the property that anytime it intersects some conjugate of P, some conjugate of some element in my peripheral family, that intersection is either finite, so we'll ignore it, or finite index. So full means it sort of takes up all but a finite amount of space in the parabolic subgroups. Okay, this is okay. All right. So that's the setup, and then here's the theorem that gives an answer to this question that I'm raising. I'm going to do something similar to what I do in this instructive example. I'm going to find a normal subgroup of G so that X mod K, a normal subgroup will be called K, so that X mod K is a cat zero cube complex. And then I'll try and spend some time telling you why I want actions like this. So here's the setup. And given that setup, there exists a finite set B contained in G, so that for any collection of normal subgroups of my peripheral subgroups P, such that two conditions hold. So B stands for bad, so we're supposed to avoid the bad set. And the second condition is what's going to ensure cube complex in the quotient. So for all sigma cube in X, if N and N P intersect stab sigma, then N fixes sigma pointwise. The second condition is the thing that's going to ensure that it's a cube complex. Okay, so what's the conclusion? Yeah, that's all I need. The conclusion is that if K is, so it's very similar to this instructive example, the normal closure of this family of normal subgroups of my P, this normal closure in G, then the quotient of X by K is a cat zero cube complex. Fullness is part of the hypotheses. And I don't know what you want about the conclusion.
I guess I didn't explicitly see it in what I did. Okay, so we're just supposed to assume that it's part of the background.
This is part of the background. Yeah. So K is not a quasi-convex subgroup. It's a normal subgroup. It's sort of the opposite of being quasi-convex. So there's nothing sort of, this is part of the input into this theorem, and I'm hiding all of the details of the proof of this. Yeah, Francois. No, I can't. That's really, so each, yeah, that's a great question, but maybe a little technical. So I'll try not to spend too much time on it. So each stab sigma has a finite index subgroup that is the set of things that's fixed the cell pointwise instead of setwise. Okay, so this assumption is really that these normal subgroups intersect stabilizers in those finite index subgroups. That you can't do that with a finite set. It's more you have to be subordinate to some finite index subgroup. Yeah, so I wanted to not introduce too much technicality there, but no, you can't put that into one. Okay, so what was my note? My notes say next, why should we care? You ask. Well, let me just make one observation that's if I look at the quotient.
If one to the point of the set B, why can't you take the B empty set?
Because if you take B, the empty set, then this might not be a cat zero cube complex.
Is really kind of set B for this example to illustrate?
No. Now, this is sort of a different sort of theorem. This is, you have to be able to find normal subgroups that have these nice algebraic conditions here. Yeah, we'll see. We will see some examples. Yeah. So
yeah, but should P be like for game filling is going to be relatively hyperbolic, or
That's part of it, and there's a lot more to it than that as well. But yeah, I mean, this is a sufficiently long Dane filling condition. So this is saying I'm going to test some normal subgroups and I'm going to look at the quotients. And in order for this conclusion, I need to have avoided some finite elements in my normal subgroups. These finite elements you should imagine are the ones that might take two sides of a square and glue them together. Okay, that might be the sort of thing that happens. Okay, and if I didn't avoid that in my normal family, then I wouldn't have got a cat zero cube complex in the quotient. Okay, now the second condition is what?
Take care of that elements that will size of it and what you.
Yeah, okay, but maybe the flag, the other conditions about flag. Yeah, the other conditions about flag, you need this as well.
Maybe for like D does not depend on normal subgroups. So like you have your G, you have your X, when B is a term.
There exists a B. Yeah, and then whenever you go and choose these subgroups that avoid B and have this property here, you get a cat zero cube complex in the quotient. B is handed to you. That's right. Okay, so
Is something that you find, like for your given group, it's like
B, well, given group and given action on the cube complex X. That's
you find that like it has all the information about it.
it has all the information. It contains all the obstructions to this not being a cat zero cube complex. Is in the B and this condition about which is what makes cubes map to cubes. No, no. It's an existence statement. There exists a statement. I mean, we have pretty explicit descriptions about what you need B to be, but we haven't written down any kind of algorithm that tells you what it is. Remember, X is likely to be a locally infinite cube complex. So I guess your input is the complex of group structure on X mod G, and yeah, we haven't thought about whether it's computable. Okay. Any other questions about the statement? Notice this is generated by elliptic elements for exactly the same reason, by the assumption that all of the elements act elliptically. So we know X mod K is simply connected. This doesn't quite, but it's not hard to see this makes it a cube complex. And the hard thing is to make it cat zero, which is to satisfy the link condition. Henri. We proving the link condition, proving the link condition, we assume that you're a cube complex in order to prove the link condition. So I don't know.
Could it be the case that maybe no such normal subgroups exist?
Yeah, sure. Absolutely. Yeah. Yes. It could definitely be the case. So here, you could take C to be the trivial group and A and B to be infinite simple groups. And then there's the only choice you have is that they're all of these A and B and NC are the trivial group. Yeah, so that's right, absolutely right. This is if you can find these normal subgroups, then we'll get this condition here. And what I'm going to spend most of the rest of the talk in is giving you situations where this is a useful thing, where there are such things, and it gives you some mileage. Okay, so what kind of mileage might you get out of it? Okay, so to pick up the sentence from 10 minutes ago, here's a quotient group, G mod K, and this naturally acts on X mod K. Okay, it is it's the deck group of this intermediate cover between X mod G and X. That deck group is in the language in the category of coverings of complexes of groups. So we like groups acting on cat zero cube complexes, and what we did, if we found such a family N sub P, is we found this quotient of G that also acts on a cat zero cube complex. And now you might hope that this quotient is better in some way. All right, so how might so a useful assumption is that elements of P are residually finite. But then residually finite groups have lots of finite index subgroups. In fact, if you give me a group B and P is a residually finite group, I can find a normal subgroup that avoids B. And then I can also pass to a further finite index subgroup that satisfies this property, because this is really the intersection of NP with this, with the actual stabilizer lies in some fixed finite index subgroup. Okay, so making this assumption means that now there will be lots of such n sub p to which we can hope to apply this theorem. And those are going to be finite index subgroups. And then if NP is finite index in P, then up to making B bigger, probably the B that's there is large enough already. This G bar is a hyperbolic group. Generally speaking, these sorts of quotients of relatively hyperbolic groups, there are natural images of the P inside of my G bar, namely P mod NP. And for large choices of B, P mod NP injects into G bar, and G bar is hyperbolic relative to P mod NP, and so on and so forth. Okay, if it's hyperbolic relative to the finite groups, then in fact it's a hyperbolic group already. So if you come with a relatively hyperbolic group with residually finite parabolic subgroups that acts in a certain way on a cat zero cube complex, now you can find a hyperbolic quotient that also acts on a cat zero cube complex. Okay, and we like that. Why do we like that? Well, here's a famous theorem of Agel. If G is a hyperbolic group, being geometrically on a cat zero cube complex, and G is virtually special in the sense of Hagelland-Wise. And this implies that G is residually finite. In fact, G embeds in some SLNZ for some large n, quasi-convex subgroups of G separable, etc., etc. Okay, so these groups are very nice. Hagelland and Wise proved many, very strong properties about virtually special hyperbolic groups. And then Agel proved this theorem and used this theorem to solve the virtual Harkin conjecture and other such things. In our setting, this action is co-compact. Okay, that's sort of obvious. The quotient space x mod k mod G bar is just the same as x mod G, which we already assumed as a space. We already assumed that was compact. Okay, so this action is co-compact. That's just clear. But it may not be a proper action. So it may not be a geometric action. Okay, so
If you have some conditions on the stabilizer, the G bar acting on x mod k, especially with sufficient separation property. Can you upgrade Agel's theorem?
that's a great question. Give me 2 minutes. Yes. Right. So I claim that the theorem there with Manning, combined with these observations and Agel's theorem, allow one to get a lot of mileage out of these sorts of ideas. But before I answer Mahan's question, let me just step back a minute and spend a couple of minutes talking about where do actions on cat zero cube complexes come from. Okay, I'm not going to spend too much time because there's a whole 2 weeks devoted to that in a month's time. But they come from something called the Segev construction, which takes what are called codimension 1 subgroups of a group and builds an action on a cube complex. In the setting of hyperbolic groups, if you take quasi-convex codimension 1 subgroups, say a finite family of them, the Segev construction gets you a co-compact action. As that was part of what Segev originally proved about his construction. So getting a co-compact action is easy. Just it means that you've taken a finite collection of quasi-convex codimension 1 subgroups of your hyperbolic group. And there are relatively hyperbolic versions of that I'll mention. Getting a proper action is much harder. Getting a proper action amounts to finding enough quasi-convex codimension 1 subgroups that you sort of cut your group up completely in some sense. So it's very natural to come across situations where you end up with actions, even of hyperbolic groups, that are co-compact but not proper. So getting properness is quite hard. There are some criteria of Bergeron-wise and Hruska-wise and so on that tell you when you've found enough, but basically it means you have to find lots of quasi-convex codimension 1 subgroups that you feed into the Segev construction. Okay, so I claim non-proper actions are a very natural thing to want to study, even in the case of hyperbolic groups. So Agel's theorem won't apply to that. So this sort of part 1 of the talk was quotients of cat zero cube complexes. Part 2 is applications, and I'm basically going to list some things that we have done with this sort of theorem and this sort of idea. Okay, great. Okay, so now here's an answer to Mahan's question. And this theorem was proved in order to prove this theorem, although we hoped it would have other applications as well. So suppose G is a hyperbolic group acting co-compactly on a cat zero cube complex with quasi-convex and virtually special cell stabilizers. In fact, it's enough to assume it about vertex stabilizers, because cell stabilizers are intersections of vertex stabilizers. Intersections of quasi-convex subgroups are quasi-convex. Quasi-convex subgroups of virtually special groups are virtually special. Okay, so that's the setup. Then G is virtually special. I'm not going to tell you today what virtually special means. Just trust me that it was worth $3 million to Ian Agel. So it's a big deal. Every time I'm talking to my daughter about some math that I'm trying to do, she says, "Is this going to win you $3 million, Dad?" Nope. Still not. So I think that's the answer that I have to your question. Yeah, she knows the answer. She's just trying to get me to admit it. Okay, so that's the first application. For the second application, I'm going to define this term from the title. So an action of a group G on cell complex X, and I mean the action to be cellular again, is relatively geometric. So 3 conditions are going to be satisfied. So it's a co-compact action. Should have read my definition. With a family P of subgroups. So this is a condition on a group and a family of subgroups, just like in the relatively hyperbolic setting. So it's a relative condition. So each P in P acts elliptically. And 3, each cell stabilizer is either finite or finite index in an element of, in a conjugate of an element of P. So if you took the empty family, then this would just be saying a geometric action. Okay, this is, and if you've never seen this before, the example to keep in mind is the coned Cayley graph of a relatively hyperbolic pair. So here you take a group G and its family of subgroups P, and you take the Cayley graph of G, and then you look at each of the cosets of each of the elements of P sitting in there as subsets, and you take each of those cosets and you cone them to a point. You add a new vertex for each coset and you cone them to a point. So now the Cayley graph is a free action, and then but there are new vertices that are stabilized by conjugates of elements of P. So that's what happens here. Those each element fixes their cone vertex, and those are the only non-trivial stabilizers. Okay, we allow something more, a little more flexible here. than that, but the action in that case would still be co-compact. Now, in fact, as long as there's a finite family P and G is finitely generated, then any such X is quasi-isometric to the coned Cayley graph. That's follows by work of Charney and Crisp. Okay, so I claim that relatively geometric actions of relatively hyperbolic groups on cat zero cube complexes are an interesting thing to study. There's a relative version of the Segeve construction. So if I have a relatively hyperbolic group, GP, in a family of relatively quasi-convex codimension 1 subgroups, and I want to assume they're full, then I'll get an action on a cat zero cube complex from the Segeve construction, and it'll automatically be compact. It'll automatically, if the codimension 1 subgroups are full, it'll automatically satisfy this condition. And this condition here is an analog of being proper. And again, that's going to be hard to satisfy. And you need results of, say, Hrusker and Wise to say when you have enough in order to get such things. Okay, so terminology. So for a relatively hyperbolic group, GP, let's say it's relatively cubulated if G admits a relatively geometric. So this is relatively geometric, I guess I should say, with respect to the family P. Okay, so if you change the family P, you'll change what it means to be relatively geometric. So if it admits a relatively geometric action on a cat zero cube complex with respect to my family P. Okay, so the power of this definition is that in a relatively hyperbolic group, the elements of P can be totally arbitrary. Any group at all could arise. There's no necessity here for these elements to act in interesting ways on cat zero cube complexes because they're fixing points. Okay, so they could be groups that don't themselves admit actions on cat zero cube complexes, but still you might hope to use a relatively geometric action to get information about the group G, sort of ignoring the inability of your peripherals to act on cat zero cube complexes. Okay, so here's a theorem. Let's get rid of Agel. I'll give you some examples in a bit. But first, so suppose I have a relatively hyperbolic pair and it's relatively cubulated. So I shouldn't have erased Agel's theorem because this is saying that many of the things from Haglund-Wise and Agel, from Haglund-Wise and Agel's theorem hold in this setting as well. So full relatively quasi-convex subgroups of G are convex co-compact. So that means that there's a subcomplex of the cat zero cube complex on which that subgroup acts co-compactly. Okay, if the elements of P are residually finite, that's what allows this theorem, this first theorem that I mentioned, to be applicable. So then G is residually finite. There's an X, and it's over there. There exists G0 and G finite index. So if I look at the quotient of zero, this is special. I haven't told you what that means. But if you don't know what it means, I just want to warn you, this is not as helpful as you might think, because this is really a complex of groups, right? D0 is not the group of this space is a fundamental group as a complex of groups. So being special, that's not maybe so helpful. It has embedded to it has a hierarchy, various things. Nice. Full relatively quasi-convex subgroups of G separable. In fact, they're virtually retract. They have finite index subgroups that are retracts finite index subgroups. So these are some of the nice conditions you get out of the virtually special machinery in the hyperbolic setting, and this is saying that they transport over into the relatively geometric setting. Okay. 7 minutes left. Okay. Fine. All right. So I'm gonna not be able to say everything I want. Let's see what. So here's a theorem due to Teddy and Thomas. That one of them will talk about in the cubes conference. The thing I like about this theorem is that nowhere in the theorem the relatively hyperbolic groups or cat zero cube complexes come in. So just take the groups, take a pair of residually finite groups. I'm not going to tell you what everything in here in the statement means, but let G be C prime 1/6 small cancellation quotient of the free product of A and B. So then G is residually finite. So as I said, the thing I like about that theorem is that it's a statement that says nothing about cube complexes or relatively hyperbolic groups. But nonetheless, the proof goes via this sort of thing here. They prove that such a G admits a relatively geometric action on a cat zero cube complex where copies of A and B inside of G are the peripheral structure. Okay. In fact, they prove something much more general than this. All right. So let me just continue with some applications. So suppose we have a relatively hyperbolic group. Now, relatively hyperbolic groups have a natural boundary, the Bowditch boundary. So let's suppose this Bowditch boundary is that of a two-sphere, and elements of P are free abelian. The example here to keep in mind is the fundamental group of a finite volume, non-compact, orientable, to make it free abelian, hyperbolic 3-manifold. In fact, conjecturally, those are the only examples. That would be a relative version of the Cannon conjecture. Well, up to virtual isomorphism. So then G is Kleinian, namely one of the ones I just said, if and only if G is relatively cubulated. Now, one direction, if it's Kleinian, then it's relatively cubulated. It almost follows immediately from work of Cooper and Futa building surface subgroups of finite volume hyperbolic 3-manifolds. You just need to interpret what they did in the relatively geometric setting to find such an action, and it comes very cheaply. In the other direction, you want to use the main theorem and results of Markovich and Hysinski, who proved this in the setting of a hyperbolic group. This explicit statement in the hyperbolic setting, so that would be where P is empty and you're expecting G to be the fundamental group of a closed hyperbolic 3-manifold, then this explicit statement is due to Hysinski, but there's related work of Markovich. There's a version of this where G acts on a cat zero cube complex geometrically. So so instead of relatively geometrically, a proper and co-compact action. So in that case, if G is Kleinian in this setting, then Cooper and Futa explicitly prove that there's a co-compact free cubulation of such a thing, and we prove the reverse direction. But if there is a cubulation, then you're Kleinian. And again, it's using these sorts of quotients and reducing it to work of Hysinski and Markovich. So that's a different version of a similar theorem. Yes. Yeah. Actually, the free abelian here is to get rid of things like wine bottles rather than closed surfaces. Yeah. If you're allowed to be the fundamental group of a closed surface, closed orbifolds is harder. Okay. I think I have 2 minutes left, so I'm going to give you another application of this kind of stuff that in a totally different direction. So now, as usual, suppose we have a relatively hyperbolic group. If G is cubulated. Here I need this to be a proper relatively hyperbolic structure. G is hyperbolic relative to itself, and that's stupid. So just exclude that. But if you don't exclude, the theorem becomes false. The action of G on a point is a relatively geometric action on a cat zero cube complex of the relatively hyperbolic pair G comma G. So if G is relatively cubulated and the fundamental group of a compact Kejia manifold, then G is virtually a surface group. If it's infinite, virtually a hyperbolic surface group. So in the case where P is empty, this is due to Gromov and Delzant. There's also work of Delzant and P. But I think I don't think what they do quite covers this. So for example, the first groups you think of that don't act nicely on cat zero cube complexes are non-abelian nilpotent groups. So the first example of a relatively hyperbolic group that you'd think of might be a non-uniform lattice in PUN1. And I said relatively geometric actions allow you to ignore the parabolic subgroups. So maybe you can hope to get more information. This says non-uniform lattice is in PUN1 with n at least 2, and at least 3 specifically, but we can get n at least 2 as well. The non-uniform ones when n is 2 are not Kejia, but we can still prove this theorem there. Those don't act in a relatively geometric way on a cat zero cube complex. Okay, I think I'm out of time, so I think I better stop. Thanks.
Thank you. Questions for Daniel?
Sammy?
If you take the hyperbolic manifold that is already known to have virtually special fundamental double it. Is there a resulting thing that it have virtually special fundamental groups?
Yes. Although I think that's not in the literature, but yes. Yeah. Sam.
In the case when PP is relatively hyperbolic, relatively cubulated, and the peripheral subgroups are initially finite, do you get that the convex co-compact subgroups are separable? I think you said that the full.
I said the full.
Quasi-convex ones are separable.
I think convex co-compact should be equivalent to full relatively quasi-convex in this setting. I haven't thought about that, but I think that should be right. Yeah, yes, that will be right.
Okay, well, if there are no other questions, let's thank Dan again.